Sorry everyone, the limit is 15 minutes for my video, but I don't have time to recondense this, so we're just going to continue on in the second video, part 2. So as I was saying, an ax minus b squared creates a double zero at x equals b over a, and this will pass through the x-axis in a quadratically fashion. So for example, if you have whatever happening, it will then go towards the x-axis and bounce right back, kind of like in a U shape, and hit the x-axis the one time there. Okay? And so when I say passes through, yes, I really mean that it bounces off. Okay? Versus an ax minus b to the exponent of 3, that creates a triple zero, which also happens still at x equals b over a, because that's basically solving just the inside the bracket part, and the exponent on the bracket determines what type of zero it is. And it will pass through the x-axis in a cubic-like manner. So pass through x-axis in a cubically fashion. So if I were to draw that, that will look like a little function, and then it goes up towards the x-axis and then bounce through in a different kind of direction. So it goes up this way and then goes curves the other way on the other side. So it's like an x, the cubic-like graph there. Okay. All right, so let's try some examples out so that you have a better understanding of what this looks like and how you actually implement this. So we have here an example of a graph that looks like this, or sorry, of the equation that looks like this, and we're going to graph it. Okay, so to graph it, we have to think about 3 things. So the first thing we're going to have to think about, and this comes from last class, which is the end behavior. If you recall, in the end behavior, we have to consider 2 things. We have to figure out how many degrees it has, which in this case, if you think about it, we've got 1x, 2x, and 3x. So in the expanded form, the degree would have, the highest degree would be x to the exponent of 3. And then we have to think of the leading coefficients. And what does that look like? Well, this is positive, this is positive, this is positive, but then it gets multiplied by a negative here. So therefore, the leading coefficient will end up being a negative value. And that's all we really care about. And so if you remember, you don't have to memorize that chart of degrees, even, odd versus positive or negative leading coefficient. We just have to think for ourselves, what type of basic function has an odd degree that looks negative? So we go back to the cubic idea or the linear idea. All right, so the linear idea would be that it goes one way through and goes out the other way. So one will go into positive infinity and one will go into the negative infinity. So they're opposites of each other. So we know that this graph is going to have one up and one down. And the reason why I'm doing it this way, because of that negative, it used to, a line would normally go this way, right? So it'd go from the negative infinity to the positive infinity, but because of that negative, there's going to be some sort of reflection. So now we've got this reversal, so it goes into positive and then into the negative. So I know this graph is going to go up here, and it's going to end up down here in the long run. Okay? So that's the first thing I need to think about when I'm graphing a polynomial, the end behavior. The second thing is what we've been talking about today, which are the x-intercepts, or the zeros. Okay? And what type of it? Not only the number of x-intercepts, but what types are going to appear. Well, in each of the brackets, we can calculate the x-intercepts. So we've got the 2x minus 1. That's going to end up producing for me an x equals 1 over 2. The bracket of x minus 4 is going to produce an x-intercept of positive 4. And then the last bracket, x plus 2, is going to produce an x-intercept at x equals negative 2. So I've got 3 x-intercepts here, and they're all singular. And how do I know that they're all singulars? Because the exponent on each of these brackets were 1, so it's like a line. So these are all going to be single zeros only. Okay, so that means I'm going to have to draw my dots at a half, which is somewhere here, 4, which is somewhere here, and -2, which is here. Okay, so I now have my 3 x-intercepts, and they're all going to look like where they're going to hit through, oops, I lost my half there, hit through, and hit through. Okay, all right, because they're single zeros. So remember, single zeros just go like a line that goes like that. Okay, and the last thing I always need as well that we didn't talk about today, but you should know from in the past, is that this graph is going to cross the y-axis at one point in time. Remember this y-axis here? So we need to also know when we're graphing the function, where exactly does it cross? So we just have to find the y-intercept. And just like in lines and quadratics, the characteristics of y-intercept is that the x value is equal to 0. So it doesn't matter if this is a polynomial, the same rule applies, is that the x value is 0 at the y-intercept. So I just plug in 0 for my x's. So I go through the calculation, -2 times 0, -1, 0 minus 4, 0 plus 2. So really y is equal to -1 times -4 times a +2, which really ends up being that the y-intercept value would be -8. So we know there's a point at 0, -8. So that's down here. So now I have all the key information I need to draw my polynomial function. I know that it's going to come from this end, so I'll go down this way, cross through my -2, going to reach my y-intercept, curve back up to hit that half x-intercept, go up, and then come down, hit my 4, and then it's going to level out towards my -infinity, and the end behavior over here, and the end behavior over there. Okay, so there's my sketch. A few things to note is you might ask, well, how do I know when to stop here? How do I know when to stop here? Couldn't it go up more? Couldn't it go down more? And you're right, you don't know that at this point. In order to, so how do I know it stops there? You don't in this class. And we're just leading you to get towards it eventually, but you learn how high this thing goes using calculus. Okay? And so therefore, we're not there yet, and so we'll leave it for calculus to tell you how do you know how far up it goes. And the same thing for here is that we don't know if maybe it went this way and then up. We don't know that, for example, just using these behaviors that we learned. Okay, but also I want you to note is that, well, the way I drew it matters. So we had a dot here, a dot here, and a dot here. Yes, we had a dot here, and we talked about the up, down, how far up and low it goes. We don't know that for calculus, but then because we know end behavior, this graph can't go like this, and it can't go like this. This is wrong. Okay, why? Is because it's too linear, and for example, like this is a straight line, whereas this is a polynomial, so it should have gone more curved and it would continue along its similar slope here. And so you just have to be careful that it doesn't all of a sudden kind of do a kink in this and it moves over that way. All right, just be careful of that. We don't want this. All right, so let's continue practicing the skill that we've been learning and apply it to a couple more examples just to make sure that you understand how this works. All right, so here we have this example here. Let's talk about the 3 features we need to think about. So the first one are the end behaviors. And the end behavior needs to think about the degree and the leading coefficient. So the degree in this one, well, there's 3 x's here and 1 x here, so the highest degree would be 4. The leading coefficient, well, this is positive and that's positive, so therefore it would be positive. And when we have an even degree and the leading coefficient is positive, we know it's going to end up looking on the same side. So it'll go up and goes up to positive infinity. Okay, so we know it's going to go here and it'll go here somewhere. All right, let's say this is the start, and this will be the end. And then the next thing we look at are the x-intercepts. And in the x-intercepts, I'm not going to have to write it all the time, but you're going to think about the number of x-intercepts and the type of x-intercepts. And so if we solve our different brackets, x plus 6, that means there's an x-intercept at -6, and the x minus 1 means that there can be an x-intercept at +1. This one here, because of the exponent was 1, it's going to be a single 0. Whereas here, this exponent was 3, so we know this is going to be a triple 0. So a triple 0 is going to look cubic, right? Versus a single is going to look very linear. So at those points, and now I'm going to do a sketch, just so that we don't always, because we don't have that calculus knowledge to know the endpoints, I'm just going to do the sketch that we have a -6 over here, and we have a 1 here. So roughly something like that. And we know that this -6 is going to be singular, so we know it's going to cross like that, versus this one will kind of curve like this, right? But we also have one more information, which is our y-intercept. So we're going to look into that. And that is always when x is equal to 0. So plugging that in, y equals 0 plus 6 in brackets, 0 minus 1 cubed. So really y equals negative 6. That's 6 times -1. Okay, so that would mean somewhere down here at -6, it's going to cross my y-axis. Okay, so then how do I draw that? Well, we said that this is going to go through here like a line. We're going to go down, and we don't, I don't want the line. We're going to go down here, cross through our -6, go up, and then do a cubic-like x-intercept, and then go up this way. All right, again, yes, I don't know how far down I should be going because we don't have the calculus knowledge just yet. Okay, so our graph looks something like this. Let's do another example just to make sure. Ooh, look at this one. So this one here has, let's go through the same procedure. We'll start with 1. We'll look at the end behavior. So what is our degree and our leading coefficient? Well, degree, we've got 3 here, and then we've got 2. So therefore, we'll end up with having a degree of 5, 3 plus 2. And then our leading coefficient, well, we've got a +2, and then we've got a -4, so you'll end up with a negative leading coefficient. And so this is an odd degree. So with odd degrees, we would normally think of like a line, but it's negative, so we'll flip it the other way. So it's going to look more like this. And so then, therefore, we know that in a quadratic, it'll go, in the quadrants, it'll go from a positive infinity to a negative infinity, like. All right. Okay, so just gonna have to be quick about this. We've got the x-intercepts. So then if you look at your things, we've got 4, and this x to the 3 is really like an x minus 0 to the exponent 3. So that would mean that there's an x equals 0 3 times. So therefore, this is a triple 0. And then the other one is 2x minus 9. And that would therefore mean there's an x-intercept at 9 over 2. And then the exponent was 2. So therefore, this is a double 0. Okay, So that means if I put my points in, I've got the 0 here, and that's going to be a triple, so I'll have that cube